Okay, in this video I'm just going to give you some situations that lead to some common equilibriums. The first one I already talked about in a previous video is going to be um, the equilibrium that's formed in saturated solutions. So imagine a solution and you added salt to it over and over again, and that salt dissolved, and there were some pluses and minuses floating around in the water. And they kept dissolving and kept dissolving. The concentration went up and up and up and up until finally a hunk of crystal salt sitting at the bottom refused to dissolve. This seems like a static situation, but it's not. It's really an equilibrium. What's really happening here is that the concentration of salt in the liquid has become high enough that it's very likely that they recrystallize onto the salt. Alternatively, this salt is still an ion that naturally wants to dissolve in this crystal, and so it is still naturally giving off its ions. The concentration is such, so the salt is still dissolving. The concentration of this liquid, or the ions in this liquid, is such that the rate of dissolving, sometimes this is called the rate of dissociation. Spelling that. Dissociation is equal to the rate of crystallization. For every ion that the solution gains from the salt dissolving, there's an ion that rejoins the crystal, and as a result, the concentration of the ion becomes constant. It's the highest we can get it, and that's why we call it a saturated solution. The next one we're going to talk about are gas phase equilibriums. Some reactions, like H2 plus I2 going to HI, two of them, can happen in both directions reliably. So I can have H's floating around and I's floating around as gases, and they can bump into each other and every once in a while form HI's instead, and then these particles can bump back into each other and form H2's and I2's again. Sorry, just paused there for a second because I saw my battery was getting a little low. Anyway, so these guys can break apart and form these guys, and these guys can break back up and form these guys. And basically what we end up with is three different types of gas molecules. They're all mixed together, flying around in some sort of closed container. You can almost imagine a balloon or something. And when the right kinds of collisions happen, they go back and forth, and maybe the concentration of these will be higher or these will be higher. But those gases are all mixed together in there in a gas phase equilibrium, where both the forward and the reverse reaction will eventually hit an equal rate. State equilibriums also are an interesting one. So here we can imagine, for example, some water in a closed system. So imagine a water bottle, and the lid is on this water bottle. That's critical. Here we have liquid water. And here we have water vapor. And the water at the surface may get enough kinetic energy to jump out of the liquid and become a gas. and we might consider that the forward reaction. And then that gas molecule might bounce around in the container a little bit and eventually lose some of its energy to the environment, and as a result want to recondense and turn back into water. The amount of vapor that exists in this situation is called the vapor pressure. That vapor pressure depends on the temperature, and it depends on the type of material. Some ideas of what can, if we make the water hotter, the vapor pressure will get higher. If we make the water colder, the vapor pressure will get lower. If we're not dealing with something like water, if we're dealing with ethanol, for example, we'll have a greater pressure than we would with water. So those are some things that will affect water vapor. But here's our equilibrium. When the rate of evaporation becomes equal to the rate of condensation, then we have an equilibrium. The last one we're going to talk about, and we'll spend the whole back half of the unit on this, is weak acids. Imagine acid like HF, or hydrofluoric acid. That acid can react with water to form hydronium and the fluorine ion. In a system, what that means then is that these two might react to form F minus and the hydronium polyatomic. So this hydrogen is being donated by this fluorine to this oxygen, but this reaction doesn't just happen in one direction. The hydronium can give that hydrogen back to the fluorine. So this hydronium can go back here, or this hydrogen from the hydronium can go back and reform into HF and leave the water molecule back as a water molecule. So the hydrogen basically can be passed back and forth. The hydrogen can go this way when we're going in the forward reaction, or the hydrogen can go back when engaging in the backwards reaction. In this case, the forward reaction would be, actually I'm not even sure which of these reactions would be favored, but both of these reactions would happen at the same time, and the concentration of HF and F minus in the solution would change to compensate for the overall natural speed of the reaction. And finally, an equilibrium would be reached where there's just as many HFs donating their protons to water as there are hydroniums donating them back to the F minuses and reforming water. So the proton can go this way or this way at the same rate, and when we hit that same rate, the system appears to become stable, and we have our equilibrium. So there's a lot more than this. This is just 4 very common equilibrium situations that we're going to explore in more detail in the rest of this unit.